So the next talk will be given by Sohan Ghosh from the Harish Chandra Research Institute, and he will lecture on the pseudonullity of fine Selmer groups of function field. Please.
Thank you for the introduction. So first, I want to thank the organizers for giving the opportunity to speak in this wonderful event. And title of my talk is, as you have seen, this on pseudonullity of fine Selmer groups of function fields. I will first start by recalling the Iwasawa-Zero conjecture. This is really classical and still unsolved. So one of the key observations of Kosan Sujata in 2005 was to connect this conjecture Iwasawa, the structure of fine Selmer groups of elliptic curves, which you will see in this slide. Then we will talk about the structure of fine Selmer groups over general periodic Lie extensions. More specifically, we'll talk about the conjecture of Kosan Sujata again, or conjecture B in this under the section of pseudonullity. Finally, we'll talk about the status of conjectures A and B over function fields in unequal characteristic as well as equal characteristic. I'll define all these things as we go along. So let me first give a bunch of notations. So P will be for me an odd prime. ZP is the ring of periodic integers. QP is a quotient field. And throughout this talk, whenever I say that M is a R module, I always mean that M is a left R module. And M square bracket P to the power R is the notation for the elements of M, which are killed by P to the power R. And M round bracket P is the union of all these P to the power R torsion points of M. For number field K, I will use the notation CLK to be the idle class group of K as the idle class group of K. So we know that this quantity is not a well-behaved quantity in the sense that there are many questions which are still unknown. For example, the questions like whether there are infinitely many class groups or quadratic extensions of class group is one or not is still not known. But what Iwasawa showed at the pre-primary part of class groups of certain extensions tend to follow a strict pattern. And this is precisely what this conjecture is about. We'll talk about in the next slide. Let me quickly recall what is the cyclotomic ZP extension of a numbered field. Is zeta P to the power n with the primitive P as a unity and keyword. Sorry. And Q zeta P infinity is the union of Q zeta Pns. The cyclotomic ZP extension of a numbered field of Q, first defined for Q and then for numbered field, is the unique extension of Q inside Q zeta P infinity, which we denoted by Q sub C by C. That's the Galois group over Q cyclotomic over S to ZP. So basically, draw it. So firstly, we have Q here, and we're defining Q zeta P infinity as the union of all this Q zeta Pns, and cyclotomic ZP extension of Q, denoted by Q suffix C by C, is the unique extension of Q. This Galois group is isomorphic to gamma, isomorphic to ZP, denoting by gamma the Galois group is cyclotomic over Q. And for numbered field K, we simply define it as the composite of these two extensions, K and Q cyclotomic. So this is again isomorphic to ZP. And one can show that there exist finite extensions Kns of K cyclotomic. That's the Galois group of Kn over K is isomorphic to Z mod P and Z. So basically this extension line is something somewhere here. And so nothing but the K cyclotomic fixed by the open normal subgroups of the Galois group of K cyclotomic over K. And this is isomorphic to Z mod P and Z. What Iwasawa showed is the following, that the size of the p-primary class group of this Ks is of the form P to the power n lambda plus mu P to the power n plus nu for n sufficiently large. And this quantities lambda, mu, and nu doesn't depend on n when sufficiently large, and these are non-negative integers. And in fact, he showed it for a general ZP extension. And for cyclotomic ZP extension, he claimed that this mu should be 0. And this is precisely what Iwasawa's mu conjecture is. So cyclotomic ZP extension, this mu has to be 0. So far, the results in the detection are for abelian number fields by Pierre and Washington in 1979, it was in 1984, in which they show that this conjecture holds if Galois group K over Q is abelian, but is still open for general number fields. And the approach taken by the experts is to use abelian varieties to attack this problem. And more precisely, we'll talk about the connection of this conjecture with the fine Selmer group. This fine Selmer group is a subgroup of the Selmer group. We have seen last talk about the Selmer groups. So basically, let me recall it briefly. What are Selmer groups? So let E over K be elliptic curve over a field K. Now for the next couple of slides, K will be a number field. Then we switch from number fields to function fields, so characteristic P. Well, we have seen the result by model and well. And for number field K, this group, the K rational points of the elliptic curve, is a finitely generated abelian group. And for a function field, this is also true. And this first proof before this result actually were Lang and Néron. And so we also said the definition that to prove this model theorem, it will show the finiteness of the Selmer group, which is defined as the kernel of this map from H1 GK. The GK is my shorthand for Galois group K bar over K. So GK is the absolute Galois group of G at K. So GK is Galois group K bar over K. K bar is the algebraic closure of K, as usual, and EK bar is the intorsion point of the elliptic curve EK bar, and GKB is the decomposition subgroup of GK at the prime V. KB is the completion of KB, K at the prime V, and AKB bar are the KV part points of the elliptic curve. And the product is taken over all the primes. This in the last lecture how it is defined. And also we saw that this EK mod NEK, the weak modular group, in fact, injects inside the Selmer group, and the quotient is the n-torsion point of the Ted-Shaver-Wedge group, which is defined as the kernel of this global term H1 GK EK bar to put all the primes H1 GKV EKB bar. So particularly if I take n to be P, and I can show that the FP dimension of the P Selmer group is greater than equal to requires upper bound on the modular length of the ends of the elliptic curve over K. And the P infinity Selmer group is defined as the direct limit of P to the power n Selmer groups over K. And now let us look at another definition of Selmer groups. So let S be a set of finite set of places of K. It contains the primes above P, the infinite places, the primes of back reduction of E over K. And one can show that this Selmer group, and also let Ks be the maximal algebraic extension of K and by infinity set S. And one can show that the Selmer group, P infinity Selmer group, the notation I'm using is here S E slash K, is the kernel of this map from H1 Ks over K. Ks over K is again shorthand for Galois group Ks over K. P infinity is a union of, so I change my notation here. P infinity is the union of P power torsion points of elliptic curve over Q bar. So maybe notation. And is H1 KVE, and direct sum is taken over the finite set S. So the difference here happens in the sense that you're taking the product of all the primes V, but we can show that actually we need to define it for finite set of primes, and there is a change in the Galois group here in the global part. Now one defines the P infinity finite Selmer group as the kernel of this map from H1 Ks over K P infinity, direct sum V in this H1 KV P infinity. So obtained by giving stricter conditions on the local terms. So the difference here happens in local terms in the Selmer and finite Selmer groups. And one can show this isomorphic to the kernel of the map from the Selmer group to the direct sum V dividing P K with density P mod ZP. So this Selmer group is in the finite Selmer group is indeed a subgroup of the Selmer group, as we can see from this exact sequence, this one. And so what the cyclotomic ZP extension, the finite Selmer group is defined as simply the direct limit of finite Selmer groups over Kns, where if you recall this Kns were finite fields over K, whose Galois group was isomorphic to Z mod P and Z. Now, Courses Sujata conjectured that the Pontryagin dual of the finite Selmer group of the cyclotomic ZP extension, which is defined as a set of continuous homomorphisms from this group to QP mod ZP, is a finitely generated ZP module. And what they surprisingly found that this has a connection with the Iwasawa-Smigol-Zille conjecture. More precisely, what they proved is the following. So let E over K be an elliptic curve, KEP. This is an extension obtained by attaching the P torsion point elliptic curve with over the field K. Assume that KEP over K is a finite P extension. Then the Iwasawa-Smigol-Zille holds for K cyclotomy. If I know only if conjecture A holds for Pontryagin dual of the finite Selmer group of K cyclotomy. So this condition, like KAP over K is a finite P extension, is satisfied trivially in the case. For example, when the P torsion points elliptic curve over Q bar is already inside K. Now, next we move on to the setting of the non-commutative reverse theory. So more precisely, we consider G to be a compact periodic Lie group. It has no element of order P, and with a closed normal subgroup H, such that the quotient G mod H, which is denoted by gamma, is isomorphic to ZP. This is the kind of setting one considers when computing the non-commutative reverse main conjecture. For example, in the paper of Course Fukaya, Sujata, Binyakov, and Kato. So one defines the reversal algebra G over ZP as the inverse limit of ZP G mod U, where the U varies over the open normal subgroups of G, and the inverse limit is taken with respect to canonical projection maps. So in particular, suppose let us take G to be H to be trivial, and one can show that this GP gamma is a really nice structure. So GP gamma is isomorphic to the power series ring over ZP, the ZPT. Let me define this, what is the pseudonull ZPG module. So if M is a finitely generated ZPG module, we say that M is a pseudonull ZPG module if the X tie groups, X tie ZPG, M comma ZPG vanishes for I equal to 0, 1. So this is one of the definitions of pseudonullity. In particular, if X naught vanishes, then one says that M is a torsion ZPG module. In addition to that, if X1 vanishes, then one says that the module is a pseudonull ZPG module. So what's the other conjecture about the structure of finite Selmer groups? About this extension is the following. Suppose that F be a number field. Assume that conjecture A holds for E over F cyclotomy. Let F infinity be an admissible periodic Lie extension of F. So admissibility, I mean there are three conditions that I want F to satisfy. So the first condition is that I want that. So firstly is a F number field F infinity. It should contain a cyclotomy ZP extension. It's condition 1. And second is a finitely many primes of F should unify in F infinity. And thirdly, the Galois group G should be a compact periodic Lie group without any p torsion. The first line of the last condition. First line of the first condition. Then we say that if it is admissible periodic Lie extension. For example, there's something to the false extension, which so examples are the extension is union of, so if I take this extension, so F to be Q mu P, and F infinity we can define as union of Q mu P n. And we should also know, and M should be P power free. So this is an example of our extension, which the admissible periodic Lie extension. So also want this admissible periodic Lie extension to be have as a, so the Galois group has dimension at least 2 as the periodic Lie group. This also wants, for example, this is also satisfied in this case of Foster extension. Then they claim that the Pontryagin of the finite Selmer group of infinity is a pseudonull ZPG module. So this is the scenario with the function number fields. Next, we'll move to function fields. So the first case is the unequal characteristic L not equal to P. So let us fix an integer, fix to integers Ln. So let L be integer prime, which is not equal to P. And F be a finite field of characteristic P. And set K to be the function field over T, over this F, finite field. Next, I will define a ZL extensions. As L is not equal to P. And then we will, in the next slide, we'll consider ZP extensions. And this is defined as follows. So first, we take the finite field of characteristic P. And we know that the Galois group F bar over F is isomorphic to Z hat. So there's a unique ZL extension inside this. So this is, we know, we denoted by AP, sorry, FL here. So this is a unique extension of F inside F bar. This Galois group is isomorphic to ZL. And we define the ZL extension as the compositum of K and FL. So this is undignified to all the primes. In fact, one can show this. And one can show this is a unique undignified ZL extension of F, of K infinity. So this is a unique undignified. If I take K and the compositum of these two fields, K infinity is the compositum of FL. And K, this is a unique undignified extension of. So this is quite contrary to the number field case, because in number field case, whenever I consider the Galois S1 Galois undignified extension is always finite. The infinity finite Selmer group in this case is defined, but it now is a elliptic curve with the function field K, not no longer the number field. So one defines the infinity Selmer group here over K, analogously as in the case of the number field. And here S is the, I haven't defined S here. So S is the finite set of places containing the bad primes of P over K. So one can define the finite Selmer group analogously as in the case of number fields, and one can again show that this is independent of S as in a number field situation. So let us talk about conjecture A and conjecture B in this situation. So with a multivariate proof that actually the conjecture A analog here holds in the L not equal to P case. And we could find the examples where this conjecture B fails using the result of Valentino and Valentino. So the trick here is that, or the strange part is that here the Kumar map is always 0. So EKB is a equivalent mod ZL, and the proof is almost similar to the number field case. So it's always 0. So I can highlight it. So here the finite Selmer groups turned out to be isomorphic to the Selmer group, in fact, in this case, L not equal to P case. So we get some strange results. And this is one of the results of work with devices, and it's in the preprint. Now we move on to the characteristic case. So let K equal to FT be a functional field of characteristic P, and we define the finite Selmer group with using flat cohomology here. So here we're dealing with the characteristic when the K is characteristic P, and the group scheme defined by P infinity is also characteristic P. So you can't use scalar cohomology here. We have to use flat cohomology. So let S be the set of finite bases as usual, containing the basis of bad reduction of P. Then we define the finite Selmer group. Also, the Selmer group is also defined using the flat cohomology here. So the S finite Selmer group we over K is defined as the kernel of the map from H1. So I'm notating by H1F to do the flat cohomology. K here, so the notation actually is H1 flat K P infinity. Actually, it is H1 flat spec K or P infinity, not just, it's not a Galois group anymore. It's H1 flat spec K P infinity. There is some V in S H1 flat spec K P infinity, and there is some V not in S H1 flat spec K V P infinity as outside this is. So in case of number fields, also case of function field not equal to P, one can show that this HI flat K P infinity. So this is if K is a number field, K is a number field or L characteristic L, characteristic K is L. And also L not equal to P case, sorry. So basically, this is equal to the Ethal cohomology, Ethal group H1K, and one can further show this is isomorphic to the Galois cohomology, H1GK. But this doesn't happen for the function field equal characteristic. This fails, this result due to Milne. So it uses flat cohomology to define this S finite Selmer groups. And now the ZP extension that we consider are K infinity are naive ZP extension, which is defined analogously as in the case of L not equal to P case. So basically, we have again finite field F and the unique ZP extension FP here, and the ZP extension. I'm creating the compositum of this extension with K, and we get the naive ZP extension over K. And the second type of ZP extension that we consider here is used by using Carless modules. So here we can get defined limit ZP extensions. What we can show is the conjectures, analog the conjecture actually holds for both these extensions under certain conditions. Let us talk about conjecture B. So something strange happens here. So unlike the number field case, here we can produce infinitely many ZP over D extensions for any d greater than or equal to 1. In fact, for any prime P of K, we can get a corresponding ZP over D extension. I'm denoting by KBT, K to power T power P, mass frac P sub D, for d greater than or equal to 1. And this extension is signified at the prime P, and it's signified everywhere else. So its notation, that is my notation is KBT. And one can show that, and we're able to show in a situation that if I take the compositum of K infinity and KDP, and suppose there's a unique prime identifies in this case, which is the case because in this extension, there's only one prime identifies in this extension, the other, and no prime identifies to K infinity. So if I'm taking this F infinity as the compositum of K infinity and KPD, and this K infinity and KPD. So A infinity. So here no prime identifies here. Totally unidentified with all the primes. And there's only one prime identifying here. This is the extension which only one prime identifies. Denoting this unity prime by VR. A T over K being an ordinary relative curve, that I mean that the p-torsional modulity curve is non-zero. As good deduction outside this set VR. One can show that the Pontryagin group of the final Selmer group is signal ZPG module, where G is the group of K infinity over F, and S is the set of finite set of primes containing the set VR. And we will also extend it for the case when I just K infinity just KDP for d greater than equal to 1 under analogous assumptions. The references for my talk are the following. So my first paper with my advisors, Ramanujan Chandrasekhar, in this it was our theory for final Selmer groups of functional global fields, which is in archive. And the second is my paper, also in archive recently. Thank you for your attention.
Thanks for the talk. Are there any comments or questions?
In case of number fields. So there is a connection between this conjecture B and generalized Greenberg conjecture, which I don't recall exactly, but actually it's motivated from the conjecture of Greenberg of pseudonullity when they consider the Galois group of the compositum of all the ZP extensions. The conjecture there should be a pseudonull ZP module. There was an intuition behind this conjecture B in some sense.
Any more comments? If not, let's thank the speaker.